Hello, this is Andrea Hendricks. Let's turn our attention now to the graphs of y is equal to a sine x and y is equal to a cosine x. And as part of that, we want to identify the amplitude and any other changes to the basic function that we see. So I have this flash applet here that will allow us to kind of take a really quick look at what's going to happen. So the variations here are based on parameters of a, b, and c. I have now my value of a is 1, b is set to 1, and c is set to 0. So right now this is nothing more than y is equal to sine x, okay? The only value that I'm going to change is the value of a. So let's look to see what happens as I change a. I increased it by 2, so notice at the bottom it's showing me what graph I'm doing, which is 2 times sine x. If I increase that to 3, now I have 3 sine x. What's happening to the graph? Can you see? Right, it is affecting the amplitude. My graph is getting taller. It's stretching vertically. In fact, that's what you learned, hopefully if you remember this, with transformations of functions. When you have y is equal to a times f of x, that factor of a does a vertical stretch if a is greater than 1. Now if a is less than 1, between 0 and 1, it does a vertical compression. That is, it kind of makes the graph fatter, if you will. And then if a is negative, it also brings in a reflection, and I'll show you that in just a minute. But you can see as we go through, 4, now my amplitude is 4. If I put in 5, so it's not changing any of the x-intercept points. Do you notice that? It's just changing my maximum and minimum points. Can go all the way up there. Now let's go back down. And okay, so here we have just y is equal to sine x. 0 is going to zero it out for a minute. Now negative sine x, do you see what happened? It reflected the graph over, because if you remember, our graph was up and over like that, right? So now we have a reflection in addition to changing the, oops, I didn't mean to go that way, changing the amplitude, okay? So really our amplitude is going to be defined by the absolute value of whatever the coefficient of the sine function is. So the amplitude is going to be the absolute value of a. Let's go back and see what happens as we go to the cosine function. So that was all sine. Now we're going to look at cosine. So this is just a graph of y is equal to cosine x. And if we increase it, same thing's happening. It increases the amplitude. My zeros of the function are the same, so my maximum and minimum values have been changed, but nothing else is really affecting the graph there. Okay, so we can kind of sum that up. We can say this: y is equal to a times sine x has amplitude of the absolute value of a. The range is going to be from negative a to a. Well, just say this, a negative absolute value of a to the absolute value of a, because a may be negative in there. And my zeros and everything else are the same. Y is equal to a times cosine x. Same thing's happening, right? Amplitude, absolute value of a. My range is from negative absolute value of a to absolute value of a. So let me show you an example. If I wanted to graph by hand y is equal to 3 times sine x. Well, what are the zeros of sine x? Do you remember my period of sine x? It looks like this, right? We have zeros at 0 and at pi and at 2 pi. So I would suggest you start by plotting just one period and putting in the key points, those key points being the intercepts first, and then think about your maximum and minimum and how they are affected. Normally, sine of pi over 2 is 1, but now we're multiplying it by 3, so we're going to have a point on our graph at pi over 2 is going to be 3. And at 3 pi over 2, it's normally what? Negative 1, but because of the amplitude change, we're going to have a negative 3 there. And so one period of this, so hard for me to draw this on the graphing tablet, so hopefully you can see it. Okay. And then we would need to repeat this pattern, right, at negative pi over 2, what's happening? We get negative 3, we know it multiples of pi at 0, and at negative 3 pi over 2 it's going to be positive 3. Okay, so there we have the graph of y is equal to 3 sine x. Now let's look at another example. Let's suppose we want to do y is equal to negative 2 times cosine x. Well, cosine x does what? If we think about from 0 to 2 pi, it starts up and goes down like that, right? Okay. So at 0, normally our graph was at 1, right? Cosine of 0 is 1. But now, since we're multiplying by a factor of negative 2, our graph is going to be reflected as well as stretched vertically. So cosine of 0, when we input, is 1, but multiplying by negative 2 takes us down to negative 2. Okay. What happens at pi over 2? Right, cosine of pi over 2 is 0, so we're going to have zeros at pi over 2 and 3 pi over 2. What about at pi? It was normally negative 1, but we're multiplying it by negative 2, so it's going to take us to 2. And at 2 pi, it was 1, so now that's going to take it to negative 2. Okay. So that is one period of the graph of y is equal to negative cosine x. So you could continue that shape. Okay. And I won't draw the rest of that, but you can draw that in. Okay. So if you have any questions on how that factor of a affects the graph of sine and cosine, please don't hesitate to contact me. Thanks.